choice education, living on the street.
Okay, so now that we've gone over most of the meat of the concepts that we're supposed to be covering, differentiability and tangent planes, now I'm going to show you a couple ways that, couple useful ways, so useful ways to rewrite our linear approximations. So there are actually three of them, so I'll go over all three. You might find it, as I said, useful when you're doing problems to think of certain things in different ways, in different rewritten ways. So first of all, I'll just write the way that we do know that we're introduced to so far. So our L of xy is equal to f of ab plus f sub x of ab times x minus a plus our f sub y evaluated at ab times y minus b. Okay, so this is the original way, and we're basically approximating our f of xy. So we're approximating f of xy for some xy point near our AB. That's where our point P is, right? So anyways, so here's the first rewrite. So number one. Here's our rewrite number one. It's basically so we're going to let our x equal a plus h. So h is how much we moved away from our original x value of a. Okay, and then we're also going so h is the distance between a and x, and likewise we're going to let y equal b plus, and we'll say k for this one. Okay, so k is the distance between y and b, or b and y, either way. Okay, so anyways, what we're going to say is that from here, we're going to kind of replace our x's with this a plus h. So anywhere we see an x in the original equation, the starred equation up there, we're going to put in a plus h. And then for the y spot, we're going to put in b plus k. Okay? And then for a and b, those just stay there. So f of ab plus f sub x of ab. And now, for the x spot, we're putting in an a plus h. And then we keep that minus a from the formula. And then we have a plus f sub y at AB. And for the y spot, we're putting a b plus k. And then our minus b comes from the formula. Okay, so as you can see, some things are actually going to cancel out. So we're left with L of a plus h, comma, b plus k is about equal to f of AB, and that should be actually just an equals to. Sorry, equals, because this is our approximation, right? So f of AB plus f sub x of AB, and see here in the next one, our positive a and negative a can cancel out, so we just get times h plus f sub y evaluated at AB, and then here we have a b minus b, so that's 0, and then so this will be times a k. Okay? Alright, so this is basically it. So that's the rewrite, the first rewrite of our linear approximation formula. Okay? Alright, now for the second one. So this is number 2, rewrite number 2. Okay, what we're going to do now is kind of say it in terms of how our function is changing. So in terms of change in f, which is our function, our original function, right? So a change in f basically means the difference between our point now, the actual value of our function now, subtracting the value that it was at that point p. Okay, so how much did the value change of the function? Also, what else can change is our x value. So the x value that we're at now minus where we were. Okay, so that would be a. So that would be the change in x. Change in y is going to be where we are now, so our y, minus where we were, which was b. That's kind of like our a, b, and f of a, b. These are kind of like our base points, the things that we're measuring our point now up against. Okay, does that make sense? So anyways, so we're going to take this and kind of implement it into our linear approximation formula. So instead of having, so we're going to start with our normal one. So f of xy is about equal to our linear approximation, which is equal to, again, I'm going to write that formula. So you guys are going to know this formula really well, maybe even by the end of this video. But anyways, so we have that, and then our last term. Okay, almost done here. There we go. Alright, so let's see what we can change and replace. So what we're going to say is that what we can do is actually like subtract this f of ab to the left side. So subtract that. Okay, so on the left side, what we get is an f of xy minus f of ab. And then on the right side, we're left with f sub x at ab. So we're just going to keep that. We can't really replace that with anything. But now we see the next term is x minus a. And x minus a can now be replaced by delta x. So that's delta x for this spot. And then plus f sub y at ab. Can't really replace those with anything. And then we see a y minus b, which can be replaced by a delta y. Okay, so that'll be, I'll just write the delta part. So delta y. Alright, so now we're almost done. And now the last step would be to see this on the left side. And we can replace the f of xy minus f of ab with a delta f, the change in f. So this is saying the change in f should be equal to the derivative with respect to x at that point times how much we change in the x direction plus the derivative or the slope with respect to y at ab times the change in y. Okay? Alright, so this is at the bottom here, this last line, that is the rewrite number 2 of our linear approximation. And for last but not least, we have our rewrite number 3, which I'm actually going to start with where we ended up at in rewrite number 2. So that would be delta f is equal to f sub x at ab times delta x plus f sub y at ab times delta y. Okay, so for this last rewrite, it's going to be actually really simple. We're just going to replace the deltas, the triangles, with d's for differential, right? So with d's. So the way we're going to do this is, so we just write df is equal to f sub x, a comma b, dx plus f sub y, ab, and dy. And d in this sense, it kind of means the same thing as delta. Delta just means change in, and d signifies a small change in something, like the differential, right? And furthermore, I mean, you could stop here as well. That's just the same thing. But I'll just show you one more step we could take is rewriting these guys, the partial derivatives, in Leibniz notation with the fancy like curly d's and stuff. So let's do that. So we have, let me get rid of that random d. Okay, so we have our normal df is equal to, instead of that, we could write df dx evaluated at ab, and then times our dx plus, and now over here we have partial of f with respect to y evaluated at ab of dy. Okay, so that's another way you could rewrite it. So this is kind of like rewrite number 3b or something. But anyways, so that's all. Finished with the rewrites, and we're finished with this section on differentiability and tangent planes. I hope that helped, and good luck on your homework.